It is seminar number 5. We will discuss Wronskians and linear dependent or independent of function. Dependence or independence of functions, right? Wronskians. And linear dependence. Okay. Okay. Let's start with task number 1. I will use this part of the blackboard. Okay, the task is determine whether the following set of functions is linearly dependent or independent on negative infinity, on the entire real line. And task question number 1, A. So the functions are, so there are 3 functions, 1 minus x, f2 is 1 plus x, and f3 equals 1 minus 3x. Are they linearly dependent or independent? Okay, so x, so we must specify some interval x. Now, so in our task, x x belongs to this interval, so means that x is any real number, right? Any real number. So this is the chalk. How to answer this question? Are they linearly dependent or independent? Okay. So we should equate the coefficients. So we should equate this to 0 and this coefficient to 0. So the polynomial, because this is the polynomial depending on x and this is the constant. So both constants should be 0. Right. If we, right. You may use the variable t. So and we will get the expression of the other coefficients in terms of C2, right? To find C3, we may add 2 equations together. C2 is t. Is C2 maybe C1? C1, right? We add them together, and we will get this. TC3, right? Mm-hmm. Mm-hmm.
And there exists, since t can be any number.
Right. Mm-hmm.
So,
and we may take it to be equal to 1, for example. Substitute 1 for t. And then, so you have proved that the following linear combination, let's write it. So if, so this is C1, C2, and C3. So you have obtained that the linear combination minus 2f1 plus f2 plus f3 is identically 0, right? We may try to check this. So if we multiply f1 by -2, we will get -2 plus 2x. I will check the solution. Plus f2 is 1 plus x, and plus 1 minus 3x. Is it identically 0? I think yes. It's right. So they are linearly dependent. Linearly dependent. Or we may show this by finding the Wronskian of these three functions. Okay, there are two forms of the Wronskian. So the Wronskian for n vector functions, right? So we may compare them. This semester, we know that the Wronskian of n vector functions is equal to the determinant of the matrix generated by these functions as columns. Right? x11, xn1 is the function, the vector function as x1, right? x1. x12 dot 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 xn2 is the function x2. And the last function is x1n, xnn. This is the function xn. Okay, and so last year I introduced the notion of the Wronskian for n functions, right? Given the functions f, so x1 of x dot 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 f n of x. How can we? So these are n scalar functions, not vector function, but these are scalar functions. And what about the Wronskian? Do you remember the formula for the Wronskian? So the functions f1 of x dot 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 fn of x are right. Then the derivatives. And f1 n minus 1. What is the relationship between these two notions? Okay, we can. So you know that we can go from nth order differential equations, scalar differential equation, to the system of linear differential equations, right? So sometimes we have something like y, the nth derivative, plus a n minus 1 yn plus a0 equals, so this is a homogeneous equation. What is this homogeneous equation? And the vector equation. Or maybe we may use x. So the function is y and the variable is x here, right? Is it clear? So we may change the name of the function. So now I use y for the function and x for the variable. And so this is the same as y as the vector equation equals a of x times y. So not a0, but a0y equals 0. How to move from one form to the other. For example, having this, we may introduce new variables, right? Y1 equals y, y2 equals y prime, y3 is y2 primes, dot, 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 and y n is y n minus 1. And rewrite this equation in the form y1 prime. Is equal to y2, right? y2 prime is y3, dot, 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 and yn prime is equal to so the nth derivative, this is minus a n minus 1 n minus 1 yn minus dot 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 minus a0 y1, right? And so if we speak about the linear independence of the solution of this nth order equation, this is the same as take the derivatives and then to speak about the linear independence of the solutions of these vector equations. And you can see that we take the derivatives, and so this is related to the fact that we take the derivatives here, right? This is the some transmission maybe from one form of the differential equation to another, vector form and scalar form.
I have a question. Do you understand how Fuller went from the second equation to the third one? Meaning,
Which point?
This part, like this part, okay, but how much?
He have substituted 1 minus x for x1, and 1 plus x for f2, and so this is the condition of the linear dependence. Then after this, he has substituted the given functions and check this equation. Okay, so in this task, it is also possible to find the Wronskian. It will be 1 minus x, 1 plus x, 1 minus 3x, then the first derivative minus 1, 1 minus 3, and the second derivative will be 0, 0, 0. So we can see that the determinant is identical 0 because it involves them, so this 0 row. Okay, so the Wronskian is 0, but this fact doesn't imply that that these functions are linearly dependent. We have discussed this situation. For example, so the example is the following. If we consider these functions x cubed and the absolute value of x cubed, these are two different functions, right? And if we consider these functions on the interval from 0 to 1, for example, these functions will be linearly dependent, right? Because, so this is f1, this is f2, and on this interval f1 is identical to f0, right? But if we consider them on the interval from -1 to 1, they are linearly independent. But however, their Wronskian is 0 because we can differentiate them. So x cubed, the absolute value of x cubed. And what about the derivatives? So we can find the derivatives. They will be 3x squared. And the derivative of this function is equal to 3x squared, the sine of x, everywhere except for the point x equals 0. And the derivative, so the determinant is 0. What does it mean? Okay, or maybe it's better to consider maybe two cases. The first case, x is greater than 0, then x is less than 0, and after this, x equals 0. Maybe it would be more clear, right? So if x is greater than 0, then the Wronskian will be this x cubed, then 3x squared, and the determinant is 0. Right? This is the first case. The second case, x is less than 0, then the Wronskian will be x cubed minus x cubed, 3x squared minus 3x squared, and the determinant is 0. The Wronskian is 0. What about x equals 0? At this point, both functions are so can be differentiated. They both have the derivatives, because this is differentiable, and if we speak about this function, we can find the derivative of this function using the definition of the derivative, and the derivative of f2 at the point x equals 0 is 0. So both derivatives at the point x equals 0 is 0, so the Wronskian is 0. So the Wronskian is identically 0, but on the interval from -1 to 1, these two functions are not linearly dependent. So this is the problem. So theorem says that if the functions are linearly dependent, then the Wronskian is identically 0, but not vice versa. Right? Converse statement is not true. If the Wronskian is identically 0, then this will not imply the linear dependence of the functions. Right? So be very careful, and maybe in this case, K-follow is right. He chose the way to find the constants of linear dependence and not the Wronskian.
So the Follow's way is not the optimal way to find this?
In this case, so if we want, okay, I think the better way is first to check the Wronskian, to find the Wronskian and check whether it is 0 or not 0. If it is 0, then you should try to find the linear dependence, the coefficients for linear dependence.
So if it's 0,
right, but if it is not 0, then the functions are not linearly dependent.
Oh, okay.
So this proves. Let's try to solve the second part of this task. So the second question. Okay, let's consider the functions. So part B will be the functions x, e to x, and x, e to x. Let's check whether they're linearly dependent or independent on the interval from negative to positive infinity x. So x is any real number. Let's try to check. Maybe
F1 equals to x, F2 equals to x, and F3 equals to x.
Right. And it's better, I think it's better to start with the Wronskian. Let's try. Let's start with the Wronskian. X e to x, x e to x, the product. Next, 1 e to x, and then e to x, 1 plus x. And the second derivative 0, e to x. Right, so e to x, and then so 1 x plus 2.
Because the last line is not 0, as you said?
Right, but no, this is not a necessary condition for the determinant to be 0. So the last row is not 0, but this doesn't prove that the determinant is non-zero. Let's find the determinant. I can see that we can move the common factor from the second column, right? So it is equal to e to x, and we have the common factor of e to x, and so e to 2x times the determinant of x, 1, 0, 1, 1, 1, x, x plus 1, x plus 2. Next, how to simplify these? Maybe use expansion. Let's use expansion along maybe the first column, for example, using the first column. So it is e to 2x. It is multiplied by x times 1, because the determinant of this matrix, is 1. Right? Next, minus 1. So x multiplied by this determinant. Next, 1 is multiplied by the determinant of the matrix. 1x plus 2. The determinant is 2. And plus 0. So the answer is e to 2x times x minus 2. It is not 0. So it is 0 at the point x equals 0, x equals 2, at just one point, but at the other points it is not 0. No, it is non-zero, and this proves that on the entire real line they are linearly independent. So two vectors may be linearly dependent at some point, at the point x equals 2, but generally they are linearly independent.
Because they're not equal to 0.
Because, right, it is not identical to 0. Right, but they are 0 at just one point. And so this proves that these three functions cannot form a fundamental solution for some differential equation, third order differential equation, because if three functions are linearly independent solutions of the of third order differential equation, then either the Wronskian is not equal to 0 at any point, or it is identically 0 at any point t, right? So it was proved during the lecture. So there is the alternative. There are only two options, only two alternatives, to be non-zero at any point on the entire real line, or to be identically 0, right? So this Wronskian is 0 at exactly one point. So these functions are linearly independent, but they can't form the basis of the fundamental solutions for the third order linear differential equation, homogeneous differential equation.
Can we say that the functions are independent?
They are linearly independent. The answer is they are linearly independent. Okay, so the answer. Okay, so we need not try to find C1, C2, C3, because since the Wronskian is not 0 at least one point, then these functions are linearly independent. The question is,
it's obvious those three functions are independent.
Right.
So if it's obvious, do we have to?
Obvious? Why obvious? Maybe not. So why obvious? So the word obvious means that it is easy to prove. obvious means easy to prove. Is it easy to prove that they are linearly independent? How to prove this? Don't know.
X gets x e to the power x by any linear combination of the other.
But this is not the proof. I don't know why. Maybe possible. So maybe x times e to x, maybe it is possible to represent this as the linear combination of these functions. So can you give a rigorous proof of this? I think not. It's better to find the Wronskian, so Wronskian proves this. But you only say this, but not proof. You just said this. This is not the proof. Maybe it seems to be easy, obvious, but it is really not. So linearly independent. Okay, just a moment. I'm trying to. Okay, now we will try to. So we have discussed several tasks, and so I will give them. Then task number 2, let it be task number 2. Prove that two solutions of two solutions of differential equation y2 primes plus p of x y prime plus q of x y equals 0 with continuous coefficients having maximum at the same the two having maximum at the same point x0 are linearly dependent. Okay, so if we have two solutions of this equation with continuous coefficients, two solutions having maximum at the same point x0 are linearly dependent. Okay. So we have two solutions. Let it be y equals f1 of x and y equals f2 of x are two solutions. We are given that these two functions have maximums, maxima at the same point x0, right? So maximum of the function is achieved at the point x0. So the point of maximum, just a moment, x0 is the point of the function f1 of x and f2 of x. And now we must prove that these functions are linearly dependent. Linearly dependent. How to prove this?
Should we take the same approach as we took there? Let's see if there's the W of that was Wronskians.
Wronskians. maybe we may do this. We may try to do this, right? Let's find. Yes, let's find the Wronskian of these two functions, f1 and f2. It will be f1 of x, f2 of x, f prime of x, f2 prime of x. Okay, and what then? What's what is the next?
Second row is always equal to 0.
Not always. At just one point x0. At the point x0. So we know that the Wronskian at the point x0 is equal to 0. What shall we do next?
Find the Wronskian at point w of x using the Liouville equation.
Liouville, right? Liouville equation, but maybe we need not compute the Wronskian. Yes, from the okay, so the proof of the Liouville's formula used the fact that the Wronskian for two functions, for the Wronskian of the functions that are which are the solutions of a linear equation has two options, right? Only two alternatives. The Wronskian is identically zero for any value of t, or it is never zero. So since it is zero at the point x0, right? So it follows that it is identical 0, and this means that these functions are linearly dependent. So for general case, if the functions are not necessarily the solutions of some linear differential equation, the fact that the Wronskian is identically 0 doesn't imply that the functions are linearly dependent, like in this situation, right? But these functions are not solutions to some linear differential equation. But in a particular case, if two functions are known to be the solutions of a linear differential equation, then okay, so the Wronskian is identical 0 and they're linearly dependent, or it is never 0, right? So it is identically 0 and these two functions are linearly dependent. It follows from the existence and uniqueness theorem, and it can be explained in some using another way, right? If we not use the Wronskian, we may consider the initial value problem. Let's find them. Okay, suppose f of x0 is a maximum, f1 of x0 is some value, right? And suppose it is equal to c times f2 of x0. So we compute these two values, and we can find c such that f1 of x0 is equal to c times f2 of x0. This is just two numbers where we know these two numbers. If they are both 0, then c, for example, is 1. If they are not 0, then we can divide. Then c is equal to f1 of x0 divided by f2 of x0. And we can consider the function f of x, which is equal to the difference. The difference f, okay, f1 of x minus c f2 of x. Consider this function. C is the function obtained from this equation, right? Let's consider this function. I state that this function satisfies this differential equation because f1 is a solution, f2 is a solution, and any linear combination is a solution of the given equation. So this is a solution. And what about the initial value problem? So this solution satisfies f of x0 equals f of x0 equals 0 and f prime of x0. There is the second order differential equation, so initial condition must include two conditions, so two restrictions on the value of the function at the point x0 and the derivative of x0. What about the derivative? 0, because x0 is a point of maximum of both functions. This means that since both functions are differentiable and they attain their maximum at this point, then they must look like this, right? The derivative of both functions are 0 at the point x0. Okay, so this is the initial conditions. And the point which is identical as 0 satisfies these initial conditions. But we know that, so by Picard-Lindelof theorem, we know that the solution exists and unique. And so this means that this function, so f of x is identical as 0, and this means that this is identical as 0, right? So this is proof without the Wronskian. It can be done in this manner, in this way. Well, how much time we have? Okay, I think so. Maybe it's time for the break, and after this we may discuss, or we may solve one more problem. Just a moment. Okay, one more task maybe, and after this, wants to solve. Right. Welcome. Now let it be for you. Okay, the task is having given three solutions of a homogeneous differential equation, find the solution satisfying the initial condition. Okay, it's task number 3. Given three solutions of a differential equation. So we are not given the differential equation, but we know that these three functions give solution. So these are three solutions of some differential equation, and the task is to find a solution satisfying the following initial conditions: y of 0 equals 2 and y prime of 0 equals 0. We are not given the differential equation, but we know that these three functions are its solutions. And you should find a solution or the solution satisfying these initial conditions. Okay, do you know what to do?
First question, if there are three solutions, does that mean the differential equation is a third order?
Maybe, right, but yes, they are maybe third order. So we need to give some third order, so it is impossible to find. Maybe they are linearly dependent or not. Are they linearly dependent or not? I think not.
No, they're not.
I think not. They're not linearly dependent, and so they are independent. So third order. So we need to.
But two of them are linearly independent. So from my guess, we're going to have two constants.
Maybe so we need one more initial condition, right? One more initial condition.
No, I think two initial conditions enough.
Not two initial conditions.
Yeah.
Enough for the second order, but we need the third. So we need the third order. So we need one more different one more condition.
So are you saying that if we have three solutions, then that means the differential equation is of the third order?
Right.
Okay.
Third order differential equation, right? But we need the third solution, right? So I will write it. So it's not enough because we have that third order differential equation. So it's I think it's 2 and y2 prime of 0 is 0. I think this this way. Right. Ashish, do you want to solve it? Okay. What shall we do to solve this? We may try to find the Wronskian, yes, but I think it will not help. Let's try to find the Wronskian. It will be x squared 1 minus x 1 minus 3x, then 2x minus 1 minus 3, and 2, 0, 0. And the Wronskian is the product of these determinants. It is 2 times 3, so minus 3 plus 3x plus 1 minus 3x. Minus 4. It is minus 4. So not 0, right? Next, what shall we do next? After this, after finding the Wronskian, it is not 0, so these solutions are linearly independent. So I think it is clear without the Wronskian because the linear. So we know the basis in the space of polynomials of degree 2. The basis is 1x and x squared, and it is easy to obtain these functions from these 3 functions. So it is easy. It is clear without the Wronskian, finding the Wronskian. But what shall we do next? We need to find the solution for which y of 0 is 2, y prime of 0 is 2, y2 primes of 0 is 0.
We assume y is equal to a times y1 plus b times y2 plus c times y3.
Yes, and right.
But
right, and then.
But the second one can never be achieved.
Why? Why not?
Because if y of 0, then it is
so
y3 is equal to 1.
Right. So I'm not right. So yes, I see. Right. The last one. Yes, if the last one is achieved, then right.
A is equal to 0.
It must be 2. Minus 2, right. I think I'm not right. Right. So there is some mistake. I don't know where. Right. So I think the mistake in the task. So I don't know exactly what's wrong. But we're trying to find. Yes. let's try to achieve this. You think that it is impossible, right? So ax squared plus bx plus c. Then the second derivative is 2a, and it is 0, so a is 0. So y prime is equal to b. B is 2. And y of 0 is equal to c. So c is also 2. Then our function is 2 plus 2x, I think. Right. And it can be represented as the linear combination of these functions, right? So it can be seen that since these are 3 linearly independent solutions, then their linear combinations, then they form the basis of the solution space. And so any linear combination of these functions will give us the solution, right? So any polynomial, and it is possible to find a polynomial in this form. Yes, I think so. Let's have a break, and after this we will discuss homework number 2. I think problems from seminar number 2, and from homework number 2, nobody have managed with this. So task number 1, part B. Check whether the following functions are Lipschitz in X in the domain t squared plus x squared less than r squared. Okay, B is the function f of tx equals t plus the absolute value of x. Okay, the task is to check whether this function is Lipschitz in this domain or not, whether or not this function is Lipschitz.
Okay.
Who can solve this?
You want us to try?
Right, welcome. Then subtract. Or turn. I got. Triangle inequality, correct. Okay, so by definition, this function is Lipschitz with the constant, with the Lipschitz constant 1. What is the definition of the Lipschitz function? Can you write the definition? Okay, follow, write the definition of the Lipschitz function. For Lipschitz function.
Function f is Lipschitz if f of t comma x, the absolute value,
right,
minus f of t comma y is
less than L. If there exists some constant L such that this inequality is satisfied. So this is a Lipschitz condition, and he found the absolute value of the difference. And by triangle inequality is less than or equal to, so it must be equal to or equal to. And here also x minus y, and so it is Lipschitz with this Lipschitz constant. Very easy. Next. Who want to solve next? So it is C. Let's check whether this function is Lipschitz or not. Whether or not this function is Lipschitz. Okay, Ashish, welcome. No. Who wants? Okay, Kafi wants. Take the chalk. What shall we do next? Yes, but this estimate will not work. Multiply and divide by, right? And divide by the sum of the squares. Divide by, it is equal to. You may try this. It will be useful. Absolute values.
Less than x minus 1. Sorry.
But this is the absolute. So the absolute values, right? Less than. It is greater than 0, but it is close to. It approaches 0 as x approach 0 or y approach 0. Okay, so this equality is correct, but we will use it to prove that this function is not Lipschitz. Right? Let's prove that this function is not Lipschitz using this formula. This is greater than 0, but it can be done as small as we want. And so if we divide by a very little constant, then this will raise unrestrictedly, right? Unbounded. It became unbounded, right? And so we can't say that it is less than or equal to x minus 0, because if we divide, for example, 1 divided by epsilon can be done as large as we want, and so this is not good. Okay, but how to prove? This is not exactly the proof. So to prove that it is not Lipschitz, let's consider some particular case. So something bad happens near 0, right? So if we consider x and y close to 0, or we may consider y to be equal to 0, we will try to find the square root of x minus 0. It is just root of the absolute value of x, and so it is the absolute value of x divided by the absolute value of x. And we can see that if x is close, x is close to 0 and y is 0, then it can't be done less than or equal to L times x. So because L must be constant, but if as this square root approaches 0, the inverted fraction, so it approaches inverted value approaches infinity. Okay, suppose, or maybe we can give some proof like this. Suppose it is possible, suppose there exists L such that it is less than or equal to L times the absolute value of x. Then we must have 1 over root absolute value of x less than L. It follows from this inequality. And so it follows that root the absolute value of x greater than or equal to 1 over L. But if x is small enough, then it is impossible. Right? Mm-hmm.
How come you took only L of x and not L of x minus y?
Y is 0.
Oh,
I will take y to be equal to 0. So it is. So I may take any value I want. So this Lipschitz inequality must be satisfied for any x and y. If it is not satisfied for some values of x and y, then it fails, right? And so if I take y to be equal to 0 and x is close to 0, then I have shown that there is no such L. And so this is the proof that the function is not Lipschitz. Okay, thank you.
I need
So
to take a PCR test. Can I go now?
Right. So you right. So now task number 3. Task number 3. Find the Lipschitz constant of the region indicated, or prove there is none. If f of x is equal to the absolute value of x, then we can see from Paulus solution that we can see that L is 1. For this function is Lipschitz, and the same reasoning shows that the Lipschitz condition is 1. This is 3a. Okay, 3b. If f of x is x raised to the power 1/3 and x is between -1 and 1, is it Lipschitz or not? No. So the same reasoning as in part number C show that it is not Lipschitz. It's not Lipschitz.
Can we try to do some of the thing I understand now better?
Okay, C. Let's discuss C. But I think E. It is. I can solve E, but it is not very easy. Maybe it is the advanced task, and maybe we will leave it. I think we will skip it. But let's discuss 1 over x. Is it Lipschitz or not? 1 over x if x is greater than 1. Is it Lipschitz or not? And find the Lipschitz constant if yes. Can you do this?
We have to use the formula.
The formula, right? Welcome, Daniel. Let's try to use the formula.
No promises.
Okay.
So via the usage of this formula, we're gonna get that 1 over x. We're gonna have
Subtract. Just subtract. 1 over x minus 1 over y.
Minus 1 over y. equals to Lipschitz of x minus y.
Mhm.
Like this.
Less than or equal to.
Yeah. And
Mm-hmm.
then, that's where I'm getting stuck. To this point, I can get.
Okay, some maybe manipulations. You may find the common denominator and
So find the common
reduce it.
denominator of this. So if it's 1 over x minus 1 over y, the common denominator is going to be, of course, x, y, and it's going to be y minus x.
And the absolute value, right? So look at this y minus x. The absolute value of x minus y is the same as the absolute value of y minus x. So these parts are the same. And now we must estimate this. So it must be less than or equal to. And we must eliminate x and y in the denominator, right? How can we estimate this? So look at the, so we're given that x is greater than 1, greater than or equal to.
First, let me just write this.
And what about the denominator?
So we can basically substitute for O.
Okay, so the absolute value of the denominator, oh, they are positive, and so the denominator is greater than or equal to 1. And so the fraction is less than or equal to this divided by 1. Is it clear? So since the denominator is greater than 1, then the fraction is less than this, right? So because if we have, so a over b, and if we compare a over b with a divided by c, so suppose b is greater than c, suppose b is greater than or equal to c, then I said that the fractions looks like this. If a and b and c are positive, right? And so since xy, since each of the term is greater than or equal to 1, then the product is greater than or equal to 1, and so the fraction is less than or equal to x minus y, and so the Lipschitz condition is 1. 1. So compare this L and 1 multiplied by x minus y.
So they're equal, yeah.
Right?
And so what? So the Lipschitz.
Not equal. So this is less than or equal to, because x, y may be greater than 1, so this fraction is maybe less than, right? But the Lipschitz condition is 1.
And what is we don't need to find the Lipschitz constant here, right?
Right, so the Lipschitz constant is 1. Well.
For 3D, when you said it's not Lipschitz, but if we check the range, it's going to be Lipschitz.
So the same reasoning as in 1c.
But in 1c,
because we divide by x raised to the power 2/3.
Yeah, but x is between -1 and 1.
Right, but it may be close to 0. And if it is close to 0, then
And could you show us how the definition will work for 3e?
Okay, 3e. So I can solve it, but so my solution is too complicated, I think. I don't want to discuss it. Maybe it is.
I'm not asking you to discuss it. Just write down how the definition will look like. Since you have to.
For functions depending on 2 variables. Right, I will write. So the proof is too complicated, so I don't want to discuss it. But the condition for the function from R2 to R, and if we want to define what does it mean that the function, what it means that the function is Lipschitz in the variables x and y. So this means that okay, the argument will be the vector x is the vector x1, x2, and y is y1, y2. And for any x and y, we must state that f of x minus f of y, the absolute value here, because this is the number, this is the number, and this is the number. This is the vector, the function from R2 to R, right? Must be less than or equal to L times the norm of x minus y. What is the norm of x minus y? It is L times the square root of x, so x1 minus y1. I think it's not good. I think y1 and x2, y2. So it will be x1 minus x2 squared plus y1 minus y2 squared. It's this. Okay, now let's go further. And now I want to discuss number 5, right? Number 5. Discuss the existence and uniqueness of solutions of the equation x prime equals root the absolute value of x, where x of 0 equals 0. So look at this function. F of x, right hand part, is equal to the absolute value, the root of the absolute value. So to satisfy, to check the hypothesis of the Picard-Lindelof theorem, we must check that this function is continuous and locally Lipschitz. But this function is not locally Lipschitz. It was proved in part C. Is not locally Lipschitz, but it is continuous. So the hypothesis of the Picard-Lindelof theorem is violated, right? And so we can't state that the solution is exists and unique. But in this case, if the function is continuous but not locally Lipschitz, it can be proved that the solution exists but not unique. Exists but not unique. In this case, it can be shown in the following way. If we take this function, the identical is 0, then it satisfies this initial condition and this differential equation. So this is a solution of the initial value problem. And we may find some other solutions. We may try to solve it. The variables are separated, and so we must solve the following differential equation. Root absolute value of x equals dt. So if we consider the case x is when x is greater than 0, we can integrate this. This will give us, so integrate both parts, and we will get 2 root of absolute value of x equals t plus c. And so we can find x, which is equal to, so the absolute value of x is t plus c squared. We can remove this absolute value. So x, plus or minus, right? X is positive, so x is this function. It looks like this. And next, if x is negative, we may try to solve, to integrate, and we will get 2 root is so minus, right, minus x t plus c, and so minus x is equal to divided by, so we must divide by 4. minus x should be positive. So it is minus, it seems to me that it is minus x plus c squared over 4. So the solutions will be I think there it looks like this. And so if we consider this initial condition, we can see that the solution exists because the identical the solution which is identically 0 is a solution, and the function going through the point, this point, for example this one, is also a solution. So the solution exists but not unique.
I think for me, after this one,
so shall we discuss other? So maybe we may discuss some other task. For example, I think 10. I think 10 is the most important. Number 10. Can two distinct integral curves, just 2 minutes to discuss task number 10, and we will stop here. So can two distinct integral curves of the given equation touch each other at some point t0 x0? Touch. Touch means that not intersect each other, not have a point in common, but they touch, so they are tangent at this point. Touch each other. t0 x0, and so this means that x of t0 equals x0. So two distinct solutions. So this means that x1 of t0 is x0, x2 of t0 is also x0, and in addition their derivatives at the point t0 are the same. Okay, so part A, if we have the equation t prime equals x prime equals t plus x squared. Okay. So the function, this function, is continuous and locally Lipschitz in x. So the Picard-Lindelof theorem is satisfied for this function, for this equation, and the initial value problem, the solution of the initial value problem is unique. But here we can see two different equations satisfying the same condition, this one. So in the part A, the answer is no. It is not possible for two different solutions of this initial value problem to touch each other. Yes? So part number B, if I have the second order differential equation. So for the initial condition, we need this, and x prime of t0 equals something, right? Some slope. Let it be c, some constant c. But x0 and c are the same for these two solutions, right? Because they touch, and we have this condition that they have the same slope at the point t0. So since the solution exists and unique, it is also impossible. And part number C, for the third order, it is possible, of course. It is possible, equals t plus x squared. It is possible for two solutions to touch at some point, because we need the second derivative. Second derivatives may be different for these two curves. So this is the solution of task number 10. So let's stop here.